But let's take out every study.
Every single post that talks about the rise of
It's like, I want to discuss like that, so you can, I want to like clarify.
All right. So we were looking at, we finished variation of parameters. We can solve any linear second order differential equation, even if it's non-constant coefficients, and even if the right-hand side is anything really at this point, because like even the ones that we ended up doing at the end had ln of t over e of t. We had one that's like 3 e of t over square root of t. Like we can have anything now. I'm not saying it'll be easy, but you know, hypothetically we can have anything. In addition to the variation of parameters, you could also use the Green's function. The nice thing about the Green's function is that it just gives you a direct answer. So your answer v1 x1 plus v2 x2 was what you would end up finding when you use variation of parameters and you go through a trouble to find what v1 and v2 are. But all of that ends up reducing to this expression here. And so you can just use this directly. There's the price you pay is it might be a little bit of work to compute this integral of the Green's function here. So this gives you just the direct answer. So you have those two ways. You have variation of parameters as well as the Green's function approach. But I'm going to take a step back before we cover systems of differential equations, which is like moving on to like, you know, how in algebra you were able to solve for x when you had one equation, but let's say you had to solve for x and y, and there's a system of equations. Now we're going to do the same thing, but now your system of equations are not just algebraic equations, but differential equations. But before I do that, I want to step back and just go into like a little bit of theory and talk more about like what's the what are some properties of the homogeneous solutions we need to make sure occur in order for us to have valid solutions to initial value problems. What is wrong with this? So suppose you have some homogeneous solution, x of t, so we have a homogeneous equation. So this is our homogeneous equation. And I'm just looking at a homogeneous equation because I wanted to point something out about our x1s and x2s. They have to be a certain thing. You can't have any old x1 and x2s. Let's say you solve this homogeneous equation, and we always said that you have two homogeneous solutions for second order equation. It's going to be x1 and x2, and then they both have two different constants that are multiplied to of c1 and c2. And if you want to solve an initial value problem where your initial condition is this and your derivative condition is this, I just wrote the purple and red, orange here. What you do is what you say here, okay, this is an initial condition on the function. We're going to plug in t naught into our solution and say that has to equal x naught, and then we take the derivative and plug in t naught, and that has to equal v naught. So you have these two equations that need to be satisfied in order for you to be able to solve for this initial value problem. You need to find, what are we doing? We're finding c1 and c2 so that you can satisfy these two initial conditions. You need two initial conditions because you need two equations for two unknowns. Your two unknowns here are C1 and C2. But I'm leaving everything very general. You've done this for very specific problems, and I'm just saying hypothetically, we don't know what our X1 and X2 are, but if we were constructing the homogeneous solution from them, then solving this initial value problem is just plugging these in. And I'm going to do elimination. So what I'm going to do is I'm going to try to eliminate the C2 term right here. That means that I need, this is x2 and this is x2 prime. So I'm going to have to multiply this top one by x2 prime, t naught. And then I'll multiply this bottom one by x2, t naught. That's going to make this term is going to have an x2 and an x2 prime. This one's also going to have x2 and x2 prime. And I'll call this 1 and this equation 2. Then you can eliminate C2. The C2 term by just doing 1 minus 2, the equation 1 minus equation 2, which ends up being like I just have the equation 1 is this thing, which I'll just see the C2s will cancel. So there's going to be this C1 I'm gonna do it like this. So I'm gonna say there's gonna be this multiplied, so I'll just do x1 t naught times x2 prime t naught. And then it's going to be minused by this down here, which is going to be like this x2 times this one. So it'd be x2 t naught times x1 prime t naught. And they both have c1, so that's why I factored out the c1 right away. This multiplied to this term and this multiplied to this c2 term will both be the same. When you subtract them, those will go away. We did that by design. And then you just have this x2 prime t naught times x naught being multiplied on there minus this x2 t naught times the v naught. And so then this eliminates the c2, so we can find c1. There's only just c1 left in this equation, and all you're just going to do is just divide. So therefore, your c1 is equal to this whole thing divided by this whole thing. Okay, that's like just, we don't know what x1, x2 are, but we just leave them general. Hypothetically, you have a general solution that has both C1s and C2 still in it, but we don't want them to stay arbitrary. If we're going to apply initial conditions, we should be able to find C1 and C2, and you could do elimination on this system of equations. You need two equations for two unknowns. If you eliminate C2, then you get C1 has to equal this. This, I'm going to point out, the top is just going to be this still. But the bottom, what do you notice the bottom is the same as? And then I'm just going to write the coefficient matrix so maybe I'll just grab it. Well, I don't know, where is it? It's probably way somewhere else. So I'll just write the coefficient matrix for the, if you were to use like the variation of parameters, this would have been this. So if you took the determinant of this, what would you get? It's called something. It's called the Wronskian, right? This bottom one, is exactly the determinant of this, right? Because x1 times x2 prime, x1 times x2 prime, and x2 times x1 prime. This is exactly the Wronskian. It's the Wronskian, but it's evaluated at the initial time t naught. The Wronskian is in general a function of t, and this just happens to be the Wronskian evaluated at t naught. And we know the Wronskian, it can be in general a function of t because look, this was a function of t when we computed this Wronskian. This Wronskian was 1, so sometimes it's just a constant. This Wronskian was 2t cubed, so that was a function of t. So in general, your Wronskian is a function of t, but in order for you to be able to solve this initial value problem for both C1s and C2s, for any initial condition, I just left the initial condition general, x of t naught is equal to x naught and x prime of t naught is equal to v naught. I'm not saying x naught or v naught or t naught or anything in particular. They could be in general anything. You need to, for this to always be able to have a way to find your constant C1, and similarly we'll see for C2, you need to have this Wronskian. So the issue is you can't have this be 0 because then you'd be dividing by 0. So, you would get C1 is undefined. So you need the Wronskian at the initial time to not equal 0 to find C1 and C2 that solves initial value problem. Okay, so you could do something similar. I'm going to delete this for a moment. You could do something similar with your in order for you to find C1, you could do like basically elimination. So I'll just copy this set of equations. I don't know if I can fit it on this side. Okay, so maybe we can barely fit it. What you could do is you could say, okay, I'm gonna have this system. Why don't I just try to eliminate C1 instead? which means that I need this x1 to also be multiplied by x1 prime of t naught. And then I need this to be multiplied by x1 at t naught. Sorry that this is like smushed, but this is at t naught. And then I'll label this as 1 and label this as 2. And then to eliminate C1, I need to do 1 minus 2 again, but this time it's been multiplied with different things. And that'll give you C2. The C1s will cancel, so you have C2 times this stuff, which is going to be x2 t naught times x1 prime. No, x2. No, it is x1. Yeah, because I'm multiplying by x1 prime. This is actually x1. No, it's x2. Sorry. Oh my gosh. So it's going to be x2 because this got eliminated, so it's just x2 and then x1 prime minus x1 gets multiplied. Multiplied by x2 prime at t naught. And they both have C2, so that's why I factored it out. And then you have on this side, it's going to be x naught, or I'll just do x1 prime at t naught times the x naught minus the x1 times t naught of t naught times the v naught. Okay, and then therefore our C2 has to equal this thing divided by this. X2 prime x1, x2 prime x1, x2 prime x1. All right. So this bottom right here is you look at this bottom right here. It's like the same as this, but instead you have x2 and x1 prime here, and then x1 and x2 prime here. So this is like the negative of the Wronskian. So basically, this is going to be like the negative of the Wronskian. So I mean, one thing I could do is I could just pull the negative and flip this up here. So the top will end up being x1 t naught at t naught v naught minus x1 prime t naught x naught. Then the bottom will just be the Wronskian. But the same idea is that to find C2, you would need also to not have a division by 0. So for both of these, for a general homogeneous solution to be able to satisfy some general initial conditions on the function and its derivative, and you have to find C1 and C2, and just leaving x1 and x2 to be anything really, we don't know what they are. In general, like this, it reveals that for you to be able to successfully find C1 and C2, you need to have these things in the denominator not be 0. And therefore your Wronskian has to be not 0 for you to be able to. So what does that mean? Your x1 and x2, which is the Wronskian is built off of x1 and x2, it's just equal to this thing. We just have to make sure those x1s and x2s are going to not end up giving you this expression becoming 0, which actually means that your x1 and x2 have to be linearly independent solutions to the homogeneous equation. They can't be constant multiples of each other. If you happen to find x1 and then an x2 that's actually a linearly dependent or constant multiple of your x1, then it's not going to capture the correct second homogeneous solution, because why would you even have another multiple of your first homogeneous solution? Because your first homogeneous solution is already an arbitrary constant times that homogeneous solution. So you'll just have a repeat of the same thing. You really need to make sure your x1 and x2 are different enough, and those different enough, and they also have to satisfy the homogeneous equation. And the difference has to mean that they're different, means that they're linearly independent. And we also saw before that the Wronskian, when we were trying to find v1 prime and v2 prime using variation of parameters, the Wronskian showed up as the denominator here. So we already knew, like, kind of back then, that there would have been problems if our W ended up being 0, right? Because here we would have had an issue of being able to find v1 prime, v2 prime. So they're connected, right? We needed W back then even to be not 0, to be able to find v1 prime and v2 prime using Cramer's rule. And it just is confirmed here that you need that also to be true if you want to solve any general initial value problem. Okay. So given a second order equation, show that the Wronskian itself satisfies a linear first order differential equation, and then solve it to get the following expression, which is called the Bell's identity. I'm going to show that in a moment, but I want to point out what is the point of this is that, okay, we talked about just before that in order to find the solution to any general initial value problem, you need the Wronskian evaluated at the initial time to equal not 0. But for any second order equation of this form, it turns out that whenever your Wronskian at the initial time is equal to 0, then your entire Wronskian will be 0 for all t. You can see that because you can obviously, if you accept that this is the solution to your Wronskian, then you know that this is going to be greater than 0 because it's just an exponential. So therefore, the condition that your Wronskian is 0 for all t is going to be this if and only if the Wronskian at the initial time is equal to 0. Because the only way you're going to get this right-hand side and this left-hand side, well, if you want this, if you're saying the Wronskian is 0 for all time, it's because this is not going to be 0. It's going to have to be that this is equal to 0. Conversely, if you make this equal to 0, since this is positive, those two are going to multiply to 0, and then this would always be equal to 0. You could also say that these go hand in hand as well. The Wronskian at the initial time not equaling to 0 will make this be something that's not 0 multiplied by something that's greater than 0 will not be 0. So that means that. And then if you have something that's not 0 for this, then since this is greater than 0, you just have to make sure this is not equal to 0. So this is a true, this is an if, these are two true if and only if statements. And it's only applies to some differential equation that's second order like this with non-constant coefficients. It turns out that the Wronskian has this property where if your Wronskian is equal to 0 at the initial time, then it will be equal to 0 for all time. So this statement up here just says that the Wronskian shouldn't be equal to 0 at t naught, but that's going to be equivalent to the Wronskian not being equal to 0 for all t. The only thing that's left is to show that this is the solution to the Wronskian. And it's going to require us to go back and look at so recall what the Wronskian is. So I'll just say the Wronskian, right, if you remember from the past, is equal to the determinant where it's like x1, x2 prime minus x2, x1 prime. And what I'm going to do is I'm going to take the derivative of this. If you have this is a true statement. I mean, that's the definition of the Wronskian. If you take the derivative of a true statement, you'll still get another true statement. So you'll say dw over dt is equal to, I'm just going to take the derivative of this. Right. And then I'm just going to do the product rule because both of these are derivatives. So it's going to be like, or functions of t. So it's going to be x prime, x2 prime plus x1, x2 double prime minus x2 prime, x1 prime. Because of the minus, I have to distribute that. So this is going to be x2 x1 double prime. And then you can see that these two cancel. And then you're left with just the x1, x2 double prime minus x2, x1 double prime. And then I'm just going to plug in. So okay, I'll just note here. We have this is a homogeneous equation. Move this down. Just say that this is actually greater than 0. But I want to point out here that from this equation, this homogeneous equation, what does x1 and x2? So I'll just rewrite this as x double prime is equal to negative p of tx prime minus q of tx. I'll just drop the t's, so I'll just say p of x prime minus q of x. The p and t are functions of t. That's just solving, just keeping the x double prime on this side. We know, though, that x1 and x2 are homogeneous solutions, so they must satisfy this equation. So that means that x1 double prime has to equal negative px1 prime minus qx1. And similarly, I'll just write it down here, x2 double prime has to equal negative px2 prime minus qx2. So that means that this x2 double prime is the same as this because it satisfies the homogeneous equation. And you're going to have a minus x2, and then this x1 double prime is the same as this right here. Okay. Then let's multiply everything out. You'll end up getting negative p x1, x2 prime. This is going to multiply and get you negative q x1, x2. This is going to be plus p x2, x1 prime. This is going to be plus q x2 x1. And then you'll see these two cancel. Okay. Then we're left with negative p, because they both have p's in it. I'm going to factor that out. And then you have x1 times x2 prime. And then minus, factor out a negative p means that this is going to be a minus x2, x1 prime. Okay. Now, just look at this and this. They're the same. They're the same, so just say this is equal to this is the Wronskian. All right, so we have now shown that the first part, that the Wronskian itself satisfies a first-order linear differential equation. So what is the linear first-order differential equation? You have this on this side, dw over dt is equal to negative pw. So the Wronskian itself satisfies a first-order differential equation. You could solve this using just separation of variables, and that'll give you the solution up there. So you'll just take the equation and separate it. dw over w is equal to negative p dt. You're going to take the integral of both sides. And you'll get ln, the absolute value of the Wronskian, is equal to negative. So we just have no idea what this p of t is. So you really have no choice but to, I guess, just write it as a definite interval. You'll say it goes from a to t of p of t dt. And then there's some integration constant that's going to pop up. We're just leaving it as a definite integral, like using fundamental theorem, just because we don't know what this p of t is. And then what we're going to do is we're going to take the e of both sides, exponential of both sides. So you're going to get absolute value of e to the, just shove this down a little bit. e to the, this whole thing, a to t, p of t, dt plus c. And then it's the same process we always do with these. It's going to be like w, drop the absolute value. You're going to have plus or minus e. I'm going to split this, so it's e to the c, e to the negative, this rest of it. And then you can redefine this as another constant c. And so we're left with the Wronskian is equal to c times e to the, what do we always usually use for a? We always use the initial t for a, right? Whenever we had this definite integral. So, we'll put t naught into that. So I'll just say this is the same as e to the integral from t naught to t of p of t dt. Now, if you plug in, if you make this t naught and say you wanted to plug in the, initial condition where t is equal to t naught, then you'll end up getting that the Wronskian at t naught is equal to c e to the t naught, that's like plugging in this t as t naught. And then you, well, I guess what I should have done is these should be s's, sorry. I always do this, right? I always use a different integration variable. So then it's clear that what we're doing is we have this, and then it's some integral of ds, but it doesn't really matter because if you're integrating over nothing, over a region, integral over just not even an interval here because it's t naught, this is going to go away. So this means that c is equal to the initial Wronskian at the initial time. So that's it. Then you know that we found the c is equal to this initial Wronskian. If you choose a to be the t naught, so then that means that your Wronskian for all time is equal to the Wronskian at the initial times e to the integral from t naught to t of p of t dt. And that's the same thing that we have up here. Okay, this is called the Bell's identity. The punchline really is I'm just using this identity to show that basically in this specific case where we have a second order equation of this form, the Wronskian at t equals 0 being equal to 0 would be equivalent to the Wronskian being 0 all the time. So let's check that at least, basically we just saw both through variation of parameters and for this problem we just saw up here that we need the Wronskian to be non-zero. Specifically for this initial value equivalent at the initial time, but it's going to be equivalent to it being non-zero for all time because of a Bell's identity here. That's going to be the pair of homogeneous solutions that will allow us to be able to solve any general initial value problem, as well as, it was important to be able to find the solution using variation of parameters. And if you're able to find x1 and x2 that has this property that their Wronskian is non-zero, those are called the correct homogeneous solutions. They're called a fundamental set, and they're going to be be the correct set of solutions that will span the space of all solutions for this differential equation. And the reason they would span is because they are linearly independent, means that they're not constant multiples of each other. You don't want them to be constant multiples of each other because you're already multiplying by arbitrary constants to them. So they'd be exact copies if they were constant multiples of each other. You need them to be different, and different means linearly independent. And then it turns out that any homogeneous solution can then be written as a linear combination of that fundamental set, where the x1 and x2 are actually called the basis vectors of the solution space. This extends to higher order equations. So if you had like multiple degree order differential equation, then you will have like multiple homogeneous solutions, x1, x2, x3, x4, all the way up to xn. You need to make sure that they're all linearly independent from each other. There is a Wronskian involved for computing, you know, that you can compute when there is more than two. So and there's like a determinant that could be 3 by 3 or 4 by 4. That's harder to compute the determinant of, but that needs to be non-zero in the case if you have higher order equations with multiple homogeneous solutions. So in problem 2.3.2, we found, let's see, 2.3.2 was somewhere where we did the reduction of order. It was up here. 2.3.2. So here I gave you one of the homogeneous solutions, x1 is equal to t, and then we went through and found that the other homogeneous solution was t squared minus 1. Let's check that these solutions were actually linearly independent, and so they were actually, you know, going to be valid homogeneous solutions to be able to solve any general initial value problem. In other words, do they actually form a fundamental set? Which of linearly independent solutions. So we're going to check the Wronskian. So how can we check that they would be fundamental set of linearly independent solutions so that their combination is a valid general homogeneous solution that can solve a given initial value problem? All you're going to do is you're just going to say, okay, I just have to check that the Wronskian of this is non-zero. So what is it? x1 is t. We said that x2 is t squared minus 1. The derivative t is 1. The derivative, this is 2t. You take the determinant, it's going to be 2t squared minus the multiplication of these two is t minus 1. This is going to give you t squared plus 1. And this will never equal 0. The reason t squared minus plus 1 will never equal 0 is because this is positive. T squared is positive. Or it could be 0. I guess t could equal, you know, if t was equal to 0, then 0 squared would equal 0 plus 1. Or you could think of this as a parabola. T squared plus 1 is a parabola that's shifted up vertically by 1, and it never will cross the x-axis. So this is never equal to 0. So therefore, x1 and x2 which in our problem is t, this set t squared minus 1, form a fundamental set of linearly independent solutions that will span the space of all solutions to this homogeneous equation. A fundamental set of homogeneous. So turns out that everything that we've been doing always guarantees that this is not going to be a problem. So, you know, when we solve the characteristic equation, when we solve the initial equation and all the solution forms we had, when we do reduction of order and we find from one homogeneous solution the second homogeneous solution, they're all designed that you would successfully get a linearly independent second homogeneous solution, you know? Okay, so that's like the thing is that you can't have two copies essentially. They need to be two different solutions. You know, they can't be constant multiples of each other. That's essentially a copy because they're already being multiplied by arbitrary constant. Okay, to be complete, let's show that two homogeneous solutions x1 and x2 are linearly independent if their Wronskian is non-zero. So like I just kind of told you that, you know, if the Wronskian is non-zero, you're able to find a solution to the general initial value problem. And I said, you know, the fact that their Wronskian is non-zero actually is the same as those two solutions being linearly independent. But I just said that, like I haven't proved that. Let's just do a simple proof. So recall that two functions are linearly dependent. So linearly independent means they're not constant multiples of each other. You can't write one as a constant multiple of the other. Linearly dependent means that they are constant multiples of each other. So that's, you know, just the terminology fact. So what I'm going to show, let's just show the, I'm going to go and do this a little indirectly. I'm going to say if x1, say your two homogeneous solutions, x1 and x2, are linearly dependent, not independent, but linearly dependent, there exists some constant C such that x1 can be written as a constant multiple of x2. Right, so if the fact that they're linearly independent, not linearly dependent, means that one of them can be written as a constant multiple of the other. X1 could be written as some C times x2. Then the Wronskian is the determinant. I guess it's not helping. X1, x2, x1 prime, x2 prime, which is the determinant of, well, we just said that x1 could be written as some constant multiple of x2 because they're linearly dependent. Then that means that x1 is cx2. What's the derivative of this? C is a constant, so it'll be x2 prime. This is derivative is x prime, x2 prime. What's the determinant of this? The determinant of this is c times x2 times x2 prime minus this right here, which is exactly the same thing. And so this is equal to 0. So whenever your x1 and x2 are linearly dependent, their Wronskian will be 0, identically, actually. It's not even like they're going to be 0 at like some x values or whatever. It's going to be 0 all the whole time. They're going to be identical. It's going to be identically equal to. So what is this? This isn't proving what we just want. This doesn't prove. Well, it appears like it doesn't. Technically, what does this prove? This proves that if x and y are linearly dependent, so I'll just like copy this. This implies that the Wronskian is equal to 0, identically. Just straight up 0. But what we want to prove is to show that two homogeneous solutions are linearly independent, then their Wronskian is non-zero. Well, if you remember from your logic, the contrapositive of this would always be true. Contrapositive is always true. But what is the contrapositive? The contrapositive is, so if A, then B, contrapositive is if not B, then not A. So I'm going to negate this. So I'm going to say not this, which means that the Wronskian is not equal to 0. I guess I'll say identically. So it could be 0 at some point. Identically means that it has to be 0 like the whole time. But this is a little better than, this is just saying it doesn't have to be equal to 0 at some points. As long as it's not 0 everywhere, then we're good. Implies that x and 2 are not linearly dependent. But not linearly dependent is the same as they're being linearly independent, right? So this is the contrapositive. Linearly independent means that they're not constant multiples. And that's exactly what we wanted to prove. So the contrapositive of what we just did proves the statement we wanted. So this is the end. So this is just saying that show that two homogeneous solutions are linearly dependent if their Wronskian is non-zero. So if the Wronskian is non-zero, implies that x and 2 are linearly independent. This already solves the state, proves the statement we wanted. So I just proved the contrapositive, but so, you know, the contrapositive is always true. For if you have a true statement, its contrapositive will always be true. So you could say, okay, if you're a cat, then you're an animal. The contrapositive is if you're not an animal, then you're not a cat. That's always true, right? Because if you think about that, if you're not an animal, then you're definitely not going to be a cat. So it's the same. The contrapositive is always true. So I just proved the contrapositive and just said this. So the converse is different. The converse is going this way. So if somebody said that Wronskian is equal to 0, implies that they're linearly dependent. That's not the contrapositive. That's going in the right direction right here. That's proving this arrow right here, going backwards. That is in general not true. And I'll write a little example here, giving you a couple of, so what would you need to be able to show that the converse is not true? You would have to provide a counterexample. So as soon as you can provide an x1 and x2, that is going to give you a Wronskian that's 0, but is linearly dependent, that disproves the converse of this. That's not important, but I'll put it here so people can see. So that completes sort of a little bit of the theory, which is that we've been finding x1 and x2s using all these processes, that, basically a recipe of sorts to be able to find them. But it turns out that all of those things we've been doing were designed to give us x1 and x2, which are linearly independent. That will be basis vectors of the space of your different solution space. And linear combinations of that will give you any general solution for the second order differential equations we've been looking at. And those linear independence of those sets, those two elements in the basis of the fundamental set can be confirmed by checking that their Wronskian, which is this determinant, is not equal to 0. And this is the proof that confirms that they must be linearly independent. Okay, so that's kind of it for that. And then we're gonna now start in the next 5 minutes a little bit of an intro to solving a system. So like I said, you may have two differential equations that are coupled. So like you have dx over dt equals to the ax plus by, but that y is actually having to satisfy this other differential equation. That's a system that you have to solve simultaneously. And so you need to find your unknowns are both x of t and y of t, but you can't solve them independently of each other because they are coupled through this differential equation, system of differential equations. So what I'm going to do is we've introduced ideas of linear algebra already, so it's not going to be much of a stretch to be able to rewrite this in matrix vector form, which is what I have said here, and hopefully that we can get to that before we need to leave. So I'm going to point out that essentially, if your x and y are your unknowns, there is a coefficient matrix here, and that coefficient matrix is, I'm going to say capital A, and then the coefficients A, B, C, and D, which are the ones that are in front of these x and y's. Okay, and then, like I said, the x and y are your unknowns, so there's a solution vector. And the solution vector we said before, is some kind of vector that I'm going to say is vector x, and it's going to have two components to it. It's going to have x and y. Okay. And then the right-hand side, so that kind of builds the the right-hand side of this. The left-hand side is this right here. I'm going to say that this is like, you could think of this as a vector of derivatives. So I'll just say dx over dt, dy over dt. And then I'm just going to extract this as basically it's like the t derivative on the vector xy, where the d dt just applies to this and applies to this, and then it'll give you this. But we just said that xy is the solution vector. So this is just vector x. And so that leaves us with, this is the same as dx vector dt. So putting all this together, your matrix vector form of this is going to equal the left-hand side is this after you condense it into a derivative of vector, and it's equal to the solution vector, the coefficient matrix, which is this purple thing, multiplied by the solution. And you can confirm due to matrix multiplication that this would be A of x plus B of y, which is this entry, C of x plus dy, which is this. So the right-hand side, when you do matrix multiplication, will give you this right here. And I could even further condense this to d of x, the derivative of the x vector is equal to capital A times vector x. This is the matrix vector form of the system right here. Okay. So in this last minute, I wanted to point out, like, if you look at this, we have some intuition. What kind of solution forms do you think x and y should be in order for this system to have any hope of being able to be satisfied? For example, let's look at the first equation. Dx over dt equals to ax plus by. I need to find a solution form for x and y such that you have hope of making the left and the right hand side equal to each other, which means that I need a solution form for x that its derivative will have something that resembles itself, x and y. Is there anything? E, yeah. You want an exponential function, because an exponential function, derivative of an exponential is an exponential. X and y will both have to be exponentials. They have to be the same exponential, though. You can't have x be like e to the 2t and y be e to the 3t. You need to, let's say x is equal to e to the 2t. You need y to also be e to the 2t. Derivative of x of e to the, with x being e to the 2t, will also pop out an x to the e to the 2t. So that's the idea. So basically, you need x and t to be both some exponential e to the lambda t, where those lambdas have to be the same in order for you to be able to get both terms on the right-hand side have two exponentials that are the same, and the derivative of that exponential is the same. U and v are going to be some constants that we're going to have to find to force this these solution forms to satisfy the system of differential equation. We have three unknowns. We have u, v, and lambda, and there's going to be some linear algebra in order for us to find those three to force it to satisfy the system. All right, I'll see you guys next week. I do have office hours right now after class in here. Thank you.